All right, so thank you all for attending this first meeting of the spring quarter of the Applied Mathematics, of the Applied PDE seminar at the University of Washington in Applied Mathematics. We have a somewhat lighter schedule this quarter with only 5 talks, but I think they're going to be all fantastic. To kick us off today, we have somebody from the University of Washington. We have Stefan Steinerberger. Stefan got his PhD from the University of Bonn in 2013. Before he continued there as a postdoc for a bit, after which he became a Gibbs instructor and then an assistant professor at Yale University, joining the University of Washington as an assistant professor last year. He is also the recipient of a Sloan Fellowship, and he has worked on a variety of different analysis-related topics. And today he's going to tell us about a PDE describing roots of polynomials under differentiation. Thank you, Stefan.
Thank you for the very kind introduction. It's very nice to meet the Applied Math Department. I wish we could meet in person, and I'm sure we will at some point. And thanks for the invitation to give a talk about this. This is fun, and it's perfectly suited for an applied PDE seminar because it's an application of PDEs in algebra. And this came as a surprise to me. And it's also now connecting to other fields that I know relatively little about, and it's sort of a fun story. And I'm curious to see how it sort of further evolves. So in this talk, I will consider polynomials of degree n having n distinct roots. And until the very end of the talk, everything's going to be real valued. So the polynomials are going to be real valued. They're going to be on the real line. They're going to have real roots. And then towards the end of the talk, I'll switch to the complex plane. And you'll see when I switch. And so my interest in all of this was motivated by the Gauss-Lucas theorem, which is a very beautiful result, which says that the roots of the derivative, so the critical points of a polynomial, are contained in the convex hull of the roots of the polynomial itself. And this is sort of a very, very nice fact, and it has a very simple proof. So this is even true in a complex plane. So sorry, I was lying just now, but okay, this is also true in a real line. And the proof is you look at sort of the logarithmic derivative, and you get essentially what you get is that if the left-hand side vanishes, this means that the objects on the right-hand side have to cancel, but you can think of the objects on the right-hand side as some sort of directed forces, right? Like they're complex numbers. If they add up to 0, then the forces have to cancel. And the moment you're outside the convex hull, essentially these Coulomb forces push you off to infinity, and they become arbitrarily small, but don't become 0. So that's sort of a relatively simple proof. And the same is, I think it's easier to see in the real line, even that once you're away from the roots, there's nothing that can be done. So this is nice because it tells you that the process of differentiation sort of moves the roots further inside. The roots don't wander off. They're trapped in a certain region in space. And you can repeat the argument, right? You can look at second derivatives, and the Gauss-Lucas theorem always applies, and always says that there's sort of a shrinking convex hull of roots. And here's an illustration. So if you have these 5 roots on the real line corresponding to a polynomial, then the roots of the derivative, the critical points, they would be located here. And you see they're sort of in the middle, but if you're closer to the left, they're a little bit more to the left because you have more electric charges on the right pushing you. And that is counterbalanced by being closer to the other electric charge. And suppose now that we have a polynomial like this, then there's sort of a basic fact, since I'm assuming that all the n roots are distinct, between any 2 roots, there is a maximum or a minimum. So that's that sort of basic real analysis. And this maximum or minimum corresponds to a root of the derivative, which means that there's a highly structured sort of system at place here, which says we have n-1 intervals between these endpoints. And each one of these intervals contains at least 1 root. However, since it's a degree n polynomial and the derivative is degree n-1, having at most n-1 roots, we see that each interval has exactly 1 root. So in particular, there's an interlacing phenomenon. So what happens really is, I did not put these slides correctly. What happens is between any 2 roots, you have exactly 1 root of the derivative. And then as you keep differentiating, this remains true. So between these 2 blank balls here, there would be another root of the second derivative. And you see they're sort of nicely trapped. They move inside. That's the Gauss-Lucas theorem. Okay, so suppose now that the roots are distributed according to some nice measure and the number of roots goes to infinity. Okay, so that's sort of the setting that I find interesting is you have some nice probability measure. And I'm not specifying what nice means, but think of absolutely continuous, compactly supported, maybe the nice density. Or think of a Gaussian, which is very nearly compact supported, right? Almost. And n goes to infinity, and you ask yourself, well, what happens then? And there's sort of a theorem that was originally conjectured around 10 years ago and then proven 5 years ago. And it's also true if the measure is actually in a complex plane. So that's a more general result. And it says the critical points of the polynomial, they're also distributed according to the same measure. And in fact, this theorem is only really interesting in the complex plane because on the real line, because of interlacing, it's clear that if you have sort of a finite sample of points distributed according to a measure, the interlacing phenomenon forces you to be sort of stuck between two. So clearly the derivatives are going to reproduce the measure. In the complex plane, this is of course more complicated. In fact, if you're real rooted, you can say something much stronger. And what you can say is that if you differentiate many, many times, for example, n over log n times, then as n goes to infinity, the roots of this derivative still reproduce the original measure. The proof's not too hard. I mean, okay, so it's a sketch of a proof, but essentially what happens if you have a nice compactly supported measure and you have n roots, then the typical gap is roughly 1 over n. And since you're interlacing, each derivative can only move the mass 1 over n to the left or to the right. So the moment you differentiate a sublinear amount like n over log n or n over log n, and let n go to infinity, at some point, you reproduce the measure exactly. There's just nothing that can happen because the interlacing traps you. And you can't escape. And so this is not too hard to see. So my question was, okay, well, what happens if I differentiate an amount that's not sublinear? What if I differentiate a polynomial of degree n a number of times proportional to the degree? So here, this is a parameter t between 0 and 1. And the idea is you let n become very, very large, and you ask yourself, what can you say about the behavior of this polynomial? Well, where are its roots? And again, you can use the Gauss-Lucas theorem to conclude that the roots are sort of trapped inside the original support. So there's something sort of should exist. And then you look at numerics. So this is actually highly advanced numerics. It's not done by me. And I'll talk about this later. This is actually, so the green line that you see here is the density of 80,000 roots that were picked uniformly at random between minus pi over 2 and pi over 2. So you see that the density is not exactly a straight line because there's some local clusters, there's some local variability in the densities because it's random points. But approximately, that's what it is. And then we differentiate 40,000 times. This gives us a polynomial of degree 40,000. And this polynomial of degree 40,000 corresponds to this turquoise or blue curve. So the roots of this polynomial are extremely structured. They're very nice. And the initial randomness sort of went away immediately. Then if you differentiate like 79,200 times, then you're left with this purple curve, which is also very, very nice. And of course, if you have the polynomial of degree 80,000 and you differentiate 79,000 times, you're left with a polynomial of degree 1,000, which has 1,000 roots. So the measure is going to shrink, right? There's only 1% of the original roots that's left. Any questions on this? I will assume that not, and I'll activate the chat as well. So feel free to type questions at any point. Good idea. Should have done this soon. So here's another example. This is so the original density has taken to be, we take a parabola and we cut it off until the integral below x squared is 1. So I don't know, you can compute what that is. And we sample points uniformly from that distribution. That gives us the green curve. Then again, if you differentiate, again, 80,000 polynomial of degree 80,000, and we differentiate again 40,000 times, and 99% of the total degree, and we get again a similar picture. We get a very nice sort of structured evolution. And it's clear that if you look at other times in between, you're going to get some sort of nice one parameter family of measures, of densities, if you want. The question is, what do they do? Here's another one that's lopsided. So this is not a symmetric one. And you see, again, a similar picture. So this is a triangular density. Again, you can play this pretty much with any density you want. And again, you get some nice evolution. So, okay. So I thought that the question had been studied very much, considering that it's polynomials. Now it turns out it's actually connected to field parts of probability. So maybe the statement should be modified a bit. Now I'll get to this, but in sort of classical analysis, you know, Polya, Hardy, Littlewood, people you would suspect of having studied these sort of questions, Erdős, Turan, Freud, right, Ullmann. This does not seem to have come up much. Polya comes close. So he has a couple of questions that are philosophically related. I don't think he has this question in particular, but he's asking very related questions about, I would say, about the roots of entire functions and derivatives thereof. However, there's one beautiful sort of classical result which says that the smallest gap grows on the differentiation. So if you have a root of degree, a polynomial of degree n, and you look at the smallest gap between any pair of consecutive roots on the real line, and then if you do the same thing for the derivative of the polynomial, that gap grows. So formally stated, if I didn't know the smallest gap as the smallest distance between polynomials, then there's a result. There's a result that was proven independently many times, and that tells you the smallest gap grows. And this is a very encouraging fact, right? Because it tells us, so we have two things. We have Gauss-Lucas telling us that the support is shrinking. And we have this beautiful inequality, which tells us that the smallest gap is sort of growing, which both combine sort of hint at some sort of regularization. Right, or at least it tells us that there's no crazy amount of singularity formation where you have points colliding very close to each other, anything like that. Right. So now what I'm going to do is, so what I originally did is I called the answer UTX. So UTX is a one-parameter family of densities. And I hope that they describe sort of the limiting distributions. And you should think of these pictures here, right? So this would be, there's UT0 is the green one, and then U05X is the blue one, and U099X is the purple one. So if you don't know what's going on, you just give the answer a name, right? And then you see what you can say about the answer. So the original density is just sort of the measure, right? That's what we start with. And what we know from counting is that if I integrate over the density at time t, the answer is going to be 1 minus t. Why is that? Well, it's because the original polynomial is assumed to have n roots. I differentiate t times n times. I'm left with a polynomial of degree 1 minus t times n. And since n goes to infinity and is sort of canceled out in the normalization, I should be left with a density that has 1 minus t. By construction, this has to be true. So what can you say about this thing? So okay, what do we know? We know that the density is 1 minus t. That's sort of the L1 norm, if you want. Then there is a beautiful fact in that you do find in books on polynomials, which says that the average of the roots remains exactly in the same place. So if the polynomials have some sort of, they have root, the original polynomial has some root somewhere, the average is a number, and the derivative also has roots, and the average of the derivatives is in exactly the same place. And you can prove this algebraically. It's not a hard proof. And that, of course, has to translate, if this limiting object UTX exists, this would have to translate into this type of conservation law. And then in a book by Rahman and Schmeisser, I think, I found another identity, and this other identity is concerned with more like a variance type functional. So you see this is a double integral over the density, and the particles at x and at y, they interact via an x minus y squared interaction. So you should think of this as a form of variance. It's essentially the variance of the density. And that also obeys a beautiful thing, a beautiful identity. So this is the same variance type object at time 0. So think of it as the variance as the original measure. And then it decays like 1 minus t cubed. That's the identity you get from the polynomials. And so just to sort of mention this at one point, of course, when time approaches 1, it means you're in the regime where you differentiate a polynomial of degree n times. Well, there aren't any roots left. So all these densities have to vanish at time 1 by polynomial, by construction. So now you can sort of use sort of standard conservation law thinking, and you can say the distribution shrinks linearly in mass, right? So there's a 1 minus t shrinking that occurs. It shrinks like its mean is preserved, and what happens is this thing shrinks like 1 minus t cubed. But each of the individual measures here only shrinks like 1 minus t. So there's a 1 minus t squared that comes from both densities shrinking like 1 minus t. And then there's an additional factor 1 minus t that comes from them moving closer to each other. You get this from sort of the conservation law, which tells you that the mass, the final mass at time t, should be distributed over an area that's proportional like square root 1 minus t. So this is what the conservation laws tell you. So okay, this was like, so 3 years ago, I think it's 3 years ago, I was sort of interested. This is sort of, you can get this from reading books. Actually, it took me a long time to find the right books, but this you can sort of find. And then I tried to sort of determine what the distribution is, and I realized that there is a very nice theorem that you can prove, which says that if this continuous evolution indeed exists, right, if UTX exists in a certain sense, then it's described by the following. So I call it a PDE, but people have yelled at me for calling it a PDE. People want me to call it an evolution equation, and the reason is that the H is the Hilbert transform. So it's you know, it's essentially, if you want, it's a non-local transport equation, right? There's a du dt, there's a ddx, and this is a nonlinear term because the Hilbert transform is a non-local operation. So PDE, or evolution equation. And this should be satisfied. So this evolution equation should be satisfied on the support of the density. Okay, and I'll tell you how to derive this PDE. It's actually a lot of fun. It's almost very classical physics. But before that, I wanna sort of motivate a little bit why it's the right equation. And I'll also tell you that it turns out to be actually. So since it's an applied PDE seminar, I will tell you that very few people have actually studied this PDE, but in light of recent developments that I'll speak about, this turns out to be actually a pretty important PDE. So I think there's a lot of work that can be done on the PDE that will also have immediate other applications. And it's a fairly nice PDE. From what I've seen, it has really gorgeous structure. So of course, you know, the first thing you do is you look for closed form solutions, right? Of course, it's hard to find closed form solutions. It's always hard to find closed form solutions, but here we have, you know, 200 years of polynomial theory at our disposal. So in particular, if we could do the following, if you could find a polynomial of our family of polynomials whose roots have a precise distribution, and all of whose derivatives also have roots with a nice distribution, asymptotically in some sense. Well, for any such family, we should be able to actually find they should satisfy the PDE, right? So, and can you find this? And the answer is yes. So there's two examples that I found fairly quickly. The first one are the Hermite polynomials. And the second one are the associated Ligier polynomials. So I will not talk about them too much, but here's the relevant fact. The Hermite polynomials, they have a very nice recurrence relation. So if I differentiate the nth Hermite polynomial, I get the Hn minus mth Hermite polynomial. There's a prefactor, and we don't care about the prefactor because we care about the roots. So we don't care about the numbers in front. So essentially what you find is you find that this family of Hermite polynomials is closed under differentiation. And this means that if the root has a limiting measure, then the limiting measure has to necessarily sort of follow the same evolution, and it does. The limiting density of these roots is, in suitable sense, is to a semicircle distribution. So Hermite polynomials satisfy a semicircle distribution. And this then, so then you just plug in and you say, you know, if I start with this semicircle, and this corresponds to a Hermite polynomial of degree n, and I differentiate t times n times, I get this Hermite polynomial corresponding to a smaller semicircle. And after rescaling, you realize you should end up with this evolution equation. And it turns out if you plug it in, it actually does solve the PDE. And the computation is quite interesting because you have to compute an arctan of a Hilbert transform of this density, but the Hilbert transform of this density is actually Chebyshev polynomials. So there's some beautiful identities that start dropping out. And you can verify this. And this is what it looks like, right? So you have a semicircle solution which shrinks and stops existing in finite time, in fact, exactly at time 1, as by construction. So the second one, oops, wrong letter. It's also an L. So that's the associated linear polynomials. You don't need to know what they are. I already forgot. The relevant thing that's important is they satisfy this recurrence relation. So again, that's sort of it's a bit more complicated because you're losing the index, but you gain in the associated index. But there is nonetheless a limiting density that they exhibit, and that's the Marchenko-Pastur distribution, which is which I knew as being relevant in random matrix theory. And that's the Marchenko-Pastur distribution. That should be another solution of the PDE if the PDE does indeed describe roots of polynomials under differentiation. And it turns out it does. So this gives you a one-parameter family of solutions of the PDE, and they look a bit like this. So here you start with sort of this big outer asymmetric hill, but then it sort of simplifies. And here's sort of assumed inversion on the right-hand side. So the right-hand side is a different parameter, which just corresponds to zooming in, I think. So we have two very nice closed form solutions. And they're indeed derived by assuming that the PDE does what I claim it does. Any questions? Okay, so let me tell you about how I derived the PDE, and it's a very hand-wavy type argument, and you'll see immediately why. I basically assume that everything that goes well, and all the error terms are okay. And to the best of my knowledge, so far there is no rigorous derivation of this PDE. It's non-rigorous, and I'll tell you exactly what happens. What I'm assuming immediately is I'm assuming that the roots crystallize. By this I mean, and maybe I should mention this right now, right? So the way I introduce the problem is you have a probability measure, you draw roots randomly from a probability measure, and then something good happens, right? What I see in practice is that the PDE describes the evolution fairly accurately, even if the initial roots are not super regular, as long as they're roughly described by the measure, of course. So if you pick them randomly from a measure, that always seems to work. If you equi-space them in a nice way with proportionality corresponding to the local density, that also works. Of course, if you start with with a big clump of say 10% of the roots in one place, probably it's not going to work so well, and it would correspond to sort of not a nice measure, right? There would be some sort of singularity in the measure. So, but in practice, it does seem to work really well. And here's my initial assumption. So assume I have UTX. So this is the density of the roots after I've differentiated a little bit. My hope is that locally, if we zoom in, locally they behave like a crystal, which in 1D is just arithmetic progressions. So this is of course not true globally, right? Not even semi-locally, because you're changing densities. But locally, if there's a density and I pick a root and I look at like the 10 nearest roots left and right, I assume that up to a small error, they form an arithmetic progression. And the idea behind this is essentially that there's a regularization phenomenon that occurs. The regularization phenomenon, as far as I can tell, is hard to see from the PDE because the PDE is a non-local transport equation. So why should it regularize? But it does. And I think that would also be interesting to see this regularization effect on the PDE, which should exhibit some sort of smoothing criteria, right? Some sort of smoothing phenomenon, like should gain of regularity. And what we see in practice is the gain of regularity is sort of instantaneous. So that's sort of interesting. Remains to be understood better. Of course, if you just plug in sort of gradient u squared and you differentiate in time, you run into sort of all sorts of complications. The integration by part gets tricky because you have an arctan and Hilbert transforms. So there's maybe some interesting Hilbert transform identities hiding that should be seen. So anyway, I'm using crystallization. And then what I'm using the following identity that's satisfied for the roots of the derivative, right? It's a cancellation of the electrostatic potential. And what I want to do is I want to take a point xk, which I overloaded notation a little bit, but I want to take a root. And I want to analyze this equation close to this root. And I want to understand what happens. So what I'm going to do is I'm going to split this up into a near field and a far field. Right, so here's, this is very big, right? I mean, I take the ones that are far away, I take the ones that are very, very close. Well, the ones that are far away are actually nice, right? Because they're really a Riemann sum to an integral, and the integral is really just the Hilbert transform. Right? It's the fact that the convolution with 1 over x is the Hilbert transform, well, and here's electrostatic convolution. So it's not a, this is how the Hilbert transform enters, and it's completely natural that it would enter this way. What remains to be understood is, what about the roots that are sort of close? They're very close, so the electrostatic potential that they exert is rather large. And there's also cancellation that occurs. And here the key ingredient is assuming that they're locally arithmetic. And if they're locally arithmetic, there is an absolutely beautiful identity. So if I plug in the assumption of it being locally arithmetic, I get some ansatz like this. Then there's an identity. This is an identity that goes back to Euler. So the electrostatic potential generated by the lattice points, 0, -1, 1, 2, -2. The electrostatic potential generated by those is actually has a nice closed form, and it's a cotangent. And of course, the cotangent blows up at all the integer points, right, when scaled like this, because that's where the electrons are. So it's a very pretty identity. So you can plug that in. And then you just sort of win. So you have a local cotangent generated. So you have a local cotangent field generated by the arithmetic progression, and you have a global far field generated from the Hilbert transform. And then you do some basic calculus to see what this actually implies for the effective movement at sort of the local scale. And that gives you sort of a driving vector field. And from this, you can write down the transport PDE. This gives you the transport equation. So that's my sketch of the derivation. You see why it would be, they're not going to be arithmetic progressions. How close are they to being arithmetic progressions? I don't know. There are recent results that sort of confirm this, though. So yeah, it's a, I would call it, a rough derivation. Though it does seem to be substantial. I mean, PDE seems to work. Okay, and okay, so this concludes. So this was the original work that was sort of done 3 years ago. Now I want to tell you about sort of more recent developments, unless there are questions, in which case I will take questions first.
I have a few questions.
Yes.
So the equation is essentially nonlinear, right?
Yes, quite.
There is not a solution. So there's no point thinking about disperse relationships or anything like that. So as t goes from 0 to 1, you have things collapse.
Yes.
What happens if I were to change the sign on t and go in the other direction?
Wow. I never thought about this. I think it might be, so I would worry about the following. So the equation seems to be smoothing. So running it backwards in time probably is extremely ill-posed very quickly.
But
my guess.
But on the other hand, is there really a problem with going to polynomials of degree higher than n?
I think so. So this is a very interesting problem, right? Because the question is, if you take an antiderivative of a polynomial, you have to ask yourself, what's the constant term, the c at the end, that you add to make sure it has n+1 roots? And this might be an ill-posed question algebraically even. I don't know. I could never find good information on this. Right, so I give you a quadratic polynomial with 2 roots. You take the antiderivative. Can I find a constant such that the antiderivative has 3 roots? And if so, can I keep playing the game? And I think actually, I think there are examples where you can do this, right? You just take a Hamid polynomial, and because of the identity I told you about, you can always find the proper constant to make it the Hamid polynomial 1 degree up, and you can get n+1 roots.
Right.
I think it might actually be a very ill-posed algebraic problem where for many polynomials, you get stuck after finitely many steps. I never found a result of this flavor. I would love to see one. I would love to see a bad result of this flavor. And I think this is coupled to the fact that the equation is smoothing, which means the inverse time evolution is ill-posed and you have exponential growth of modes. Very exponential.
Well, I wouldn't. I mean, given that the equation is essentially nonlinear, I wouldn't expect it to have exponential growth. I would.
No. Sorry, no. I mean, you have sort of in the sense that the Fourier coefficients grow very quickly. The high frequency, with the analog of high frequency Fourier coefficients, like you have growth moving to high frequencies.
Given the example, you have Hermite and associated Laguerre. I mean, it's maybe hinting to that if you properly renormalize, then a lot of the ill-posedness could be taken away.
I don't think so. I think what you're saying is absolutely correct around special solutions like Hermite and like Jana will talk about this. I think the linearization around those solutions should be very nice. Algebraically, it's beautiful. It's actually, I can give you full linear, I can give you a spectral decomposition of the linear operator. Like, it's gorgeous. I think for general solutions, it's going to be a lot harder. And I think I'll get to this in the 10 minutes or so. Okay. Why I think this is a lot harder for general solutions.
Okay. Thank you.
But yeah, the inverse evolution, I would love to see. I would love to see a statement that algebraically, that at some point, it's a game with finitely many steps for almost all initial root distributions or something. I think it's very special that you can keep going.
So, well, last question. So, there's really nothing problematic with reversing t as long as I don't go past t equals 0.
What? So you mean?
So I can start at t equals 0 and do the regular time evolution to t equals 1 and see the collapse.
At time 0, the solution's gone. There's nothing left.
Oh, right. Sorry, I've got t equals 1 and 0 reversed.
Okay.
But I could start at t equals 0.5.
Yes.
And going back to t equals 1 is not a problem.
It might be. It might just be that there is no function, no initial measure that gives you that evolution at time 0.5, like the heat equation, right?
So I see how there's a problem from the polynomial question point of view, but I mean, definitely the plots that you showed of the shrinking, it doesn't seem to be a problem to go back.
Well, I mean, I could say the same for the heat equation, right? I could say it looks like going forward, it's a beautiful evolution, but going back, it's an absolute nightmare. So I think it's very similar to this, but I'm guessing at this point. I have no.
Yeah. Of course, there's an obvious loss of information because your support is shrinking.
The support is shrinking. The roots are regularizing.
Yeah.
However, I do love the question. I think on the algebraic side, this might be an absolutely fantastic problem. Like actually proving that. Yeah. So thank you for reminding me about this. I love this problem a lot. It's, okay. So a year ago, I got curious about seeing solutions of the equation. So I teamed up with Jeremy Hoskins, who implemented a fast multiple method to differentiate polynomials of degree 100,000. And here's a picture of him walking a cat on a leash. It's more fun than what you see on his professional homepage. I have permission to use this photo. And he used this, and we looked at so all the pictures you saw in the beginning of the slides were done by his program, which I think he will send you if you send him a nice email. And what we saw at the end, we always saw semicircles. So just before this sort of the evolution stopped existing, what we saw were semicircles or scaled semicircles like ellipses, asymptotically. And so we started looking at this, and we were actually able to prove it in a certain setting. And the setting is the following. So suppose you have a random variable that has all moments finite and is normalized to expectation 0 and variance 1. Pick a random polynomial, and the randomness here is generated by picking n roots, IID, from this measure. Fix an integer L, and then differentiate a lot of times. And by a lot of times, I mean n minus L times. Okay, so fix L to be 20. Pick a polynomial of degree n, differentiate n minus 20 times. And you will get a random polynomial of degree 20. Now, it turns out as n goes to infinity, this polynomial of degree 20 will start to look like the 20th Hermite polynomial. It's a universality phenomenon for high derivatives of random polynomials. If you differentiate a random polynomial often enough, it starts becoming Hermite. So the formal statement would be that if you rescale it properly, you zoom into the proper length scale, then it converges to a random shift. So gamma n is here a normal distribution. It converges to a random shift of the alpha Hermite polynomial. And of course, Hermite polynomials have a semicircle density, and this explains why there's semicircles at the end. Right? Because what we're seeing is we're seeing the roots of things that are approximately Hermite polynomials. And recalling the statement I made in the beginning, the statement I said in the beginning was that if I pick random roots, so if I have a polynomial, then the average of the roots stays preserved under differentiation. So if I pick n random roots following this distribution, then their average undergoes a shift, right? It's not exactly zero. It's randomly shifted to the left or to the right, and this has to be preserved under differentiation. That explains why there's a random shift here. It's to compensate the central limit theorem, which gives you this randomness. So the proof of this is actually quite nice. I don't have the sketch here. The proof of this is based on proving certain concentration results for elementary symmetric polynomials, which we haven't found in the literature. We found something similar, but was quite different. And it's actually a proof by induction. And it uses relatively little, I would say. So what you see rather quickly is essentially that the randomness overpowers everything, and that I can see the statement. Suppose you have n random variables, and you apply the kth elementary symmetric polynomial, then the kth elementary symmetric polynomial of this n random variables is essentially determined by the mean and the variance if k is small and n goes to infinity. And that's because there's a recurrence relation where you get out, so it's essentially the kth Hermite polynomial of suitable rescaling. And that we thought was quite fun. And it's clear that if you have an argument like this, the proof has to be algebraically simple. And it is. It's a short proof. And then a following interesting thing happened. So this is half a year ago now. So there was a new paper on the archive, and I like reading all sorts of papers, especially when they're analysis of PDEs or classical analysis. And this one had a title that I didn't quite understand, and an abstract I didn't quite understand, but I still scrolled through. And around page 19, I see the following. So this looks an awful lot like the PDE I've shown you. An awful lot. So it's actually, it's the same PDE in a different coordinate system. Now, the same PDE in a different context, or supposedly different context, that's probably not a coincidence. And so the paper itself is concerned with free probability, which is, I'd heard the name, but I never heard even the definitions before seeing this paper. And it's about an operation on measures that was introduced by Voiculescu. It's very nice convolutional measures. So so the way people explain it to me is like you have standard convolution, and standard convolution corresponds to sums of random variables, right? If I have densities and I convolve them, I get the result of summing random variables corresponding to these densities. And this is somehow the analog in the non-commutative setting. That's what people told me. And in particular, since the two PDEs are the same PDE in a different coordinate system, if you write this down, and I did write it down, you get the following amazing result. You get that the evolution of these densities for polynomials, that the evolution of these densities in a proper different coordinate system corresponds to free convolution of the initial measure with itself many times. And what's remarkable here is that k can even be a real number. So it's a fractional free convolution. And for classical convolution, this is not hard to see, right? It's just you can take a Fourier transform, and then you take an appropriate power of the Fourier transform, and you transform back. For fractional free convolution, this is a much harder statement that I think was only shown in the 90s, and many orders of magnitude more difficult. So even the existence of this object is highly non-trivial. So this would have a large number of consequences for our problem. right? It would tell you that you can use free probability theory, which I don't know nearly as much as I should. It's not even close to anything I ever studied or worked on. But they have various types of conservation laws that remain preserved under free convolution. So you have these types of conservation laws. So this should generate you infinitely many conservation laws for the PDE. So maybe the PDE is completely integrable in some suitable sense. I don't know. Maybe not. I don't have a good understanding of these things. It certainly confirms that the PDE is probably extremely interesting. So I will claim here in bold that it's infinitely many conserved quantities. What precise this means, and under which conditions that remains to be seen. So there's also a recent paper by I should mention, by Gauss-Lucas and Hoskins. So this my original derivation is purely formal, right? My derivation of the PDE of this thing is completely formal. I showed you the derivation is completely formal. It gives you a PDE. Then Shlyakhtenko and Tao have a derivation of their PDE. Which is here, and that is also a completely formal derivation. So again, assuming that things are okay, that things work well, that things are nice. So it's a formal proof if you want, but there's now one proof, and in some case, under some assumptions in some setting. So another amazing thing is that there's something known as Voiculescu's free central limit theorem, which is the free analog of the classical central limit theorem. If I convolve a measure with itself many, many times, I get a Gaussian. If I free convolve a measure with itself many, many times, I get the semicircle. And of course, if k is very, very large, this corresponds to time being extremely close to 1, which is why Jeremy and I saw semicircles at the end of the evolution. And of course, Jeremy and I have a proof now that's sort of completely elementary, just based on polynomials. So I don't know what this implies for free probability. In particular, that there's some hope of making our proof actually quantitative. So maybe this would imply quantity. So the problem is I don't know anything about free probability because it's so foreign to anything I know. So I don't even understand what the proper landscape is there. Okay, and then what happened is the day after. So this was September 3rd, September 4th. There's this paper that goes on the archive, and again, it's a bit too far removed from my expertise, but the authors tell me that in a certain sense, this proves that in the bulk of the measure, my assumption of things crystallizing is established in this paper. It's open in the edges. So the edges where you have the triple point, you have the interface, it's a bit harder apparently. And then more things happen. So October 27, so Jeremy and Sarah Gauss-Lucas put up a paper where they construct, so that they give a rigorous proof under some assumptions of the formal statement. They studied a complex case, which I'll talk about in a bit. They construct many examples, which is quite nice. So that's a very nice paper, which I hereby recommend to everybody. I have very great pictures as well. I mean, it's quite beautiful. And then another result, which is really fantastic, is a paper by Kiselev and Tan. And what they do is they take the entire problem, they put it on the circle. So instead of polynomials, they have trigonometric polynomials on S1, which can be identified with the torus, right? So instead of polynomials, you have trigonometric polynomials. And you ask yourself, what happens with trigonometric polynomials under differentiation? They derive the same PDE with the same trick. You can derive the same PDE, and it's more or less the same PDE, except that the Hilbert transform becomes the Hilbert transform on S1, so it gets a cotangent instead of a 1 over x. And what they do is they prove the PDE. So they rigorously derive it, and they control all the error estimates. So I think it's 80 or 90 pages. It's extremely involved. It does all the details. It's extremely rigorous. It's the only case where there's a completely rigorous derivation of the PDE. They prove convergence rates, they prove smoothing, they prove everything. And what's really remarkable is that it's much better than anything that exists on the real line. And what's remarkable is that the fractional Laplacian appears very naturally as a byproduct. I think this is, of course, really beautiful. And maybe I should also mention that the arctan Hilbert transform U over U, it may seem strange, but it appears quite natural in the following case, right? What is Hilbert transform U over U? Well, take U, take your function U. Take the unique harmonic extension to the upper half plane. That's given by U plus I times the Hilbert transform of U. So arctan of Hilbert transform U over U is actually nothing but the phase of the complex conjugate. So what the equation does, it's a non-local transport equation where the speed of transport is governed by the derivative of the phase of the complex conjugate. So you have sort of a complex analysis dynamic system coupled in the background that goes to sort of generate the flow. And I would love to have a better understanding of this. I don't. So here's now what's left to do, right? So a couple of things are left to do. I would like to have so of course there's not a connection between free probability and PDEs. I think it remains to be seen which side benefits more, but I think it's a very nice PDE or non-local evolution equation, and there are many things that can be done using just PDE techniques. I mean, Kizelev and Tan don't use any free probability. I'm not even sure there is free probability in that setting that they study. Maybe not, probably not. So I think what would be nice is to have a PDE understanding using PDE techniques of this. So that somehow it's clear that the PDE has to have a solution because of free probability, but it's not clear what this means in terms of PDE techniques. So conservation laws, what does this mean? I don't know. I mean, as a matter of fact, usually for these, if you have infinite many conservation laws, probably the first two tell you something, or the first three, then they don't tell you much anymore. But what does this mean? Now here's something that I think is really fun from a PDE perspective, which is if you take the semicircle solution and you linearize around it, that linearization seems to be nice. And in fact, Chebyshev polynomials seem to diagonalize it. So I think there's hope of actually getting fairly concrete understanding of the linearization. And that would naturally lead to stability results, right? If you start with something that's close to a semicircle, you should stay close to a semicircle. And then maybe that would lead to very quantitative statements about the evolution of the PDE close to a semicircle. That would be nice. Same for Marchenko-Pastur, although maybe the linearization around Marchenko-Pastur is not as explicit. Though if there's any justice in the world, it might still be nice. But for the semicircle, it's Chebyshev polynomials. I mean, so here's another question. So Jeremy actually has this algorithm to compute derivatives of polynomials. So I think it seems like this would give you a method how to compute free fractional convolution. So I don't know how people compute free fractional convolution in real life, right? Well, if you want to have examples for a paper, if you want to study certain cases, I don't know how people compute this, but this algorithm gives you a very fast way of computing what seems to be the right thing. And finally, so I've talked about the real case. I've talked about the complex. I've talked about the trigonometric polynomials. What about the complex case, right? And I'll be brief because I'm running out of time. There is a PDE, but it's a bit trickier. Well, it's sort of the same PDE, except Hilbert transform, you have a Stieltjes transform, you have a non-local transport equation, and people have sort of studied this because it starts becoming like a Burgers equation. Like it's the complex Burgers equation. Here's an example from a paper of O'Rourke and Williams. So the red dots are the roots of a polynomial of degree, I think, 150, and the blue crosses are the roots of the derivative. And you see very clearly, this looks like flows of particle in a vector field, right? Taken at short consecutive times. And what Sean and I did is we tried to understand whether there's anything nice happening if you assume the initial distribution is radial. Do you get any nice PDEs? And it turns out you get an absolutely fantastic PDE. And the PDE is very simple. It's a PDE on functions on the positive half line. And essentially what happens is you have a transport equation, and the speed of transport is given by the average value so it's given by the average density from 0 up to the point where you consider the transport. And it doesn't matter what happens on the right. It does not play a role. It just doesn't play a role. And that's because some complex analysis integrals cancel. So it's determined by what happens between itself and 0 and not what happens before. So I think that's an absolutely gorgeous transport equation that must have nice properties. It has one funny closed form solution, which is just 0 and 1, and it's 1 at a shrinking interval. And this turns out to be actually meaningful in the polynomial context as well. This corresponds to random Taylor polynomials. So random Taylor polynomials have exactly the same density. So constant density. Here you see constant in the radial part. So the density is like 1 over r in the complex plane. And they're given by, you just take a Taylor polynomial and you put random Gaussians here. Then that's clearly a polynomial family that's preserved under differentiation, right? If I differentiate this t times n times, I get this a polynomial from the same family. And it turns out there's a limiting distribution for what the density of the roots looks like for this. It's a 1 over c singularity, and that's exactly why everything works out. And the paper of Kaputschkin and Hoskins has more examples of such evolutions. And with this, I'm 1 minute over time. Sorry about this, and thank you very much.